That is the crystal structure of NaCl, that is sodium chloride crystal, is cubic FCC. Here they gave as FCC, coax-centered cubic. The density of the sodium chloride is 2.18 gram per centimeter cube, and atomic weight of sodium is 23. Atomic weight of chlorine is given 35.5. Calculate its lattice constant. Also they gave N is equal to 6.02 into 6.02 into 10 to the power 23 gram per mole. So solution, molecular weight of NaCl is N is equal to 23 plus 35.5 is equal to 58.5. Density rho is equal to 2.18 gram per centimeter cube, and Avogadro number N is equal to 6.02 into 10 to the power 23 per gram mole. For the cubic FCC crystal, number of molecules per unit cell N is equal to 4. That you need to remember. When FCC comes, then what is the number of molecule per unit cell? When SCC, simple cubic cell comes, crystal comes, then what will be the number of molecule per unit cell? And when BCC crystal, what is the number of molecule per unit cell? So for that you need to see the previous video in which I mentioned all those things. So for in this case, FCC crystal they gave, so N is equal to 4, and lattice constant A is equal to N divided by capital N into rho to the power 1/3. You need to substitute all this value. N is equal to 4 into 58.5 divided by 6.02 into 10 to the power 23 into rho is 2.18 to the power 1/3. When you solve, you will get 5.63 into 10 to the power minus 8 centimeter, that is 5.63 Armstrong. As we know, 1 Armstrong is equal to 10 to the power minus 8 centimeter. Now we are going to calculate the packing fraction and density of a sodium chloride from the following data. Radius of sodium ion is 0.98 Armstrong degree. Radius of chlorine ion is 1.81 Armstrong degree. Atomic mass of sodium is equal to 22.99 AMU, that is atomic mass unit. Atomic mass of chlorine is 35.45 AMU. So solution, the Na plus and Cl minus ion touch along the tube sides, therefore lattice parameter is equal to radius of Na plus plus radius of Cl minus. So they gave two radiuses. We need to find first the lattice parameter, which is equal to 2 times 0.98 plus 1.81, which is equal to 5.58 Armstrong degree. Now packing fraction is equal to volume of ion present in the unit cell divided by volume of the unit cell. So that is 4 into 4/3 pi r cube of sodium plus 4/3 pi r cube of chlorine divided by A cube, which is equal to 16 pi upon 3 into substituting the radius of 0.98 of cube of sodium and 1.81 cube for chlorine divided by 5.58 cube, which is coming out to be 66.3%. Now density, we know that mass upon volume. Therefore density is equal to mass of unit cell divided by volume of the unit cell, which is equal to 4 into 22.99 plus 35.45 into 1.66 into 10 to the power minus 27 divided by 5.58 into 21 minus 10 the whole cube, which we will get as 2234 kg per meter cube. Aluminum mass FCC structure, its density is 2700 kg per meter cube. Calculate the unit cell dimension and atomic radius. Atomic weight of aluminum is they also gave as a 226.9. The solution for the cubic FCC crystal, number of atoms per unit cell N is equal to, as I also told you, molecular weight of aluminum is denoted by capital N is equal to 26.98. Density rho is equal to 2700 kg per meter cube, and Avogadro number N is equal to 6.02 into 10 to the power 26 per kg mole. Density formula we know, rho is equal to Nm upon capital N into H. So lattice constant A is equal to Nm upon capital N into rho to the power 1/2. Just substitute all this value. 4 into 26.98 divided by 6.02 into 10 to the power 26 into 2700 to the power 1/3. When you solve, you will get 4.05 into 10 to the power minus 10 centimeter, that is Armstrong. So 4.05 Armstrong degree, since 1 Armstrong degree is equal to 10 to the power minus 10 meter. Now the atomic radius in FCC is given by, we know the relation between R and lattice constant A. R is equal to A upon 2 root 2. So R is equal to 4.05 upon 2 root 2 angstrom is equal to 1.425 angstrom degree. Determine the lattice constant for FCC lead crystal of radius 1.746 angstrom degree. For the cubic FCC crystal, the lattice constant is given by A is equal to 2 root 2 R, and they already give R is equal to 1.746 angstrom degree. Since no other parameter is involved, we will not convert angstrom into meter. We will keep it as it is, so that our answer we will get in angstrom degree. So A is equal to 2 root 2 into 1.746 angstrom degree. It is equal to A is equal to 4.94 angstrom degree. This is very important numerical from MCQ point of view. Sodium crystallizes in cubic lattice. The edge of the unit cell is 4.3 angstrom degree. The density of the sodium is 960 kg per meter cube. Its atomic weight is 23. What type of unit cell does sodium form? So molecular weight of sodium N is equal to 23. Density they gave as it is equal to 963 kg per meter cube. Avogadro number we already know. N is equal to 6.02 into 10 to the power 26 per kg mole. And now lattice constant A is equal to 4.3 angstrom degree. We will convert it into meters. So 4.3 into 10 to the power minus 10 meters. The density is given by rho is equal to Nm upon capital N into A cube, where N is the number of atoms per unit cell. So N is equal to, N will determine what kind of cell it is, whether it is a simple cubic, whether it is a body centered, or it is a space centered. So we need to find the number of atoms per unit cell. N is equal to capital N, so A cube upon capital N. Substituting the value 6.02 into 10 to the power 26 into rho, value of rho they gave as 963, and into A cube 4.3 into 10 to the power minus 10 the whole cube divided by 23. So when you solve, you will get N is equal to 2. The number of atoms per unit of the sodium is 2, and sodium is B.C. Very important. The number of atoms per unit cell is 2, then it is a B.C. If it is 4, then it is FCC. The lattice plane of a crystal have intersect 2, 3b and 6c on the axis. Find the Miller indices. This is very important from exam point of view. Ratio of the axis PA is to QB is to RC is equal to 2A is to 3B is to 6C. PQR means 2 is to 3 is to 6. Now in Miller indices, we need to find the reciprocal force. So P inverse, Q inverse, R inverse is equal to 1 by 2, 1 by 3 is to 1 by 6. Now next step is to multiply by the LCM of the denominator. So LCM of the denominator is 6. So we multiply by 6. Therefore, P inverse, Q inverse and R inverse will come as 3 is to 2 is to 1 is equal to, that is the HKL. Therefore, the Miller indices are 3 to 1. Another numerical, in a trigonal crystal, find the length of the intercept of a plane on the axis if the Miller indices of the plane are 1, 2, 3. HKL here they give 1 is to 2 is to 3. PQR is equal to H inverse, K inverse, L inverse, that is 1 by 1 is to 1 by 2 is to 1 by 3. Next step is to multiply by the LCM of the denominator. So LCM of the denominator will come as 6. So multiply the entire system by 6, we will get P is to Q is to R is equal to 6 is to 3 is to 2. Since it is a trigonal crystal, we will get A is equal to B is equal to C. Therefore, the length of the intercept on the axis is 6 is 3A and 2A. In a simple cubic crystal, if the lattice constant is A, then find first the distance between the lattice planes 1 to 1 and the ratio of 0, 1, 0 and 1, 0, 1 lattice interval. In a simple cubic crystal solution, we are going to find the distance between two consecutive lattice planes. HKL is, we already know, BHKL is equal to A upon under root H square plus K square plus L square. For 1, now we are going to find for 1 to 1 lattice plane. B 1 to 1 is equal to A upon under root 1 square plus K square plus 1 square is equal to A upon root 6. And for 0, 1, 0 lattice plane, B 0, 1, 0 is equal to A upon under root 0 square plus 1 square plus 0 square is equal to A. And for 1, 0, 1 lattice interval, B 1, 0, 1 is equal to A upon under root 1 square plus 0 square plus 1 square, which is equal to a upon root 2. Now we need to find the ratio. Therefore d010 divided by d101 is equal to a upon root 2, which is equal to root 2. This is again one of the IMPs from MCQ point. In a simple cubic lattice, find the density of lattice point for the plane of Miller indices 1, 1, 0. When the lattice constant is 2 angstrom decay. What is given? A is equal to 2 angstrom decay, and we need to find the density of the lattice point. For that, we need first distance between the lattice point 1, 1, 0 is d110 is equal to a upon under root h square plus k square plus l square, which is equal to a upon under root 1 plus 1 plus 0. A upon root 2 is equal to 2 upon root 2 angstrom degree is equal to 1.414 into 10 to the power minus 10 meters. Number of lattice points or atoms per unit cell of a simple cubic lattice. Here they give simple cubic lattice. So n is equal to 1. And volume of the cubic cell, you should be thorough with what is the number of lattice points for cubic simple cubic lattice, A-centered and for B.C. Accordingly, the numerical will change. And according to the what they ask in the examination, if it is simple cubic, then write n is equal to 1. If it is body centered, then write the number given for body centered, and if it is face centered, then its number you need to write, change, and the rest of the thing will remain the same. Volume of the cubic cell is equal to A cube is equal to 2 into 10 to the power minus 10 the whole cube, which is equal to 8 into 10 to the power minus 30 meter cube. And density of the lattice points delta is equal to n into d upon d, which is equal to 1 into 20. Already n is equal to 1, therefore n into 1.414 into 10 to the power minus 10 divided by 8 into 10 to the power minus 30, which is equal to 1.17 into 10 to the power 19 per meter square. Copper has a SEC cell with atomic radius 0.1278 nanometer. Find the interplane spacing of 200, 120 and 220. This is again important MCQ. The lattice constant for FCC structure is given by A is equal to 2 root 2 R. Already they gave R is equal to 0.1278 nanometer, nanometers 10 to the power minus 9 meter. Therefore, A is equal to 2 root 2 into 0.1278 into 10 to the power minus 9 meter. Only so we will get 0. A is equal to 0.369 into 10 to the power minus 9 meter, or we can simply write 3.69 angstrom degree. Now the interplane spacing is given by T of square is equal to A upon under root h square plus k square plus l square. For D200 is equal to 3.69 divided by under root 4, that is 2 square plus 0 square plus 0 square, which is equal to 3.69 divided by root 4, which you will get as 2. So 3.69 divided by 2 is equal to 1.21 angstrom degree. For D120 is equal to 3.69 divided by under root 1 plus 4 plus 0 is equal to 3.69 divided by root 5 is equal to 1.65 angstrom degree. And for D220 is equal to 3.69 divided by under root 2 square plus 2 square plus 0 square, which is equal to 3.69 divided by root 8 is equal to 1.30 angstrom degree. In a tetragonal lattice, A is equal to B is equal to 0.25 nanometer and C is equal to 0.18 nanometer. Reduce the spacing between 1, 1, 1 plus. Given A is equal to 0.25 nanometer, B is equal to 0.25 nanometer, and C is equal to 0.18 nanometer, which is already given, nanometer to the power minus 9. And spacing we need to find for 1, 1, 1. That is d x square is equal to 1 upon under root a square upon h square plus b square upon h square plus b square upon l square nanometer. We will keep the answer in nanometers, so there is no need to convert it into meters. Dx square is equal to 1 upon under root 0.25 the whole square upon 1 square plus 0.25 the whole square upon 1 square plus 0.18 the whole square upon 1 square. For solving, you will get dx square is equal to 1 upon under root 0.28254 nanometer. Dx square is equal to 1 upon 0.5314 nanometer. It is nothing but when you solve it, you will get dx square is equal to 1.881 nanometer or 1.881 into 10 to the power minus 9 meters.